Hello. So this is an example of plotting a typical polynomial using calculus. And I wanted to sort of put together a whole bunch of things I've been covering in both my Calc 1 classes, both applied calc and regular calc. So I'm giving this example. Some of you may have seen it before. First is this thing I call quick plots. That is not calculus, but I start off by factoring the polynomial, and I can just go ahead and then plot. I have a second order root at 0 and a first order root at 1 and -1. And then because there's no leading negative sign, I'm starting from up here. If there had been a leading negative sign, I would have started from down here, but we don't have to. We're starting from up here. And then we just dive down through. First order root you cut through, second order root you bounce off, first order root you cut back through. And so before we even start, we know what the answer is going to look like. We know we have a kind of W shape, which is typical of a 4th degree polynomial. It's really balanced. A lot of these W curves look like this, or they look like M's. Whoops, wrong shape. It should be an M shape. Okay, but the humps don't have to be symmetric, but they are. Because the roots are symmetric, the humps will be symmetric. So we know all that. And we're going to now erase all that and pretend we don't know it. But we already know the answer before we start. Now we're going to start and pretend we didn't know that. All right. So there's, first of all, the whole first and second derivative thing, which is the first derivative. Most students don't have any trouble with this step. And then they may or may not have trouble with the factoring step. Like, for example, I just had trouble with the factoring step. All right. If I factor out a 2x, I get 2x squared minus 1 over here. And you can hit that with the quadratic formula, or if you are really good with factoring, you'll recognize this structure. Okay, so either way, you don't have to recognize how to factor that. You can just say, you know, 2x squared plus 0x minus 1. And then the roots are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is a very complicated way of saying plus or minus square root of 8 over 4. So you can take a 4 out of there. Plus or minus 2 root 2 over 4. So it's plus or minus root 2 over 2, which is 1 over root 2. So that's all perfectly good. You can do that. But I'm not going to do it that way. I happen to factor it. So this tells me that x equals 0 is an option. This tells me root 2x is equal to 1, or x is equal to 1 over root 2 is an option. And this gives me x equals minus 1 over root 2 similarly. Okay, so I'm going to just keep this as here. Okay, so those are the first derivative, what we call critical points. And in a typical calculus class, you might deal with them right now, but I'm just going to leave them. And I'm going to go to the next step. Okay, so this guy's 6x squared is equal to 1, so x squared is 1/6. So this gives me x is equal to plus and minus 1 over square root of 6. So I'm erasing a lot of the work that you would leave on your page as a student, but I'm erasing it so that you can see the results and in one eye shot. Okay, so you have 3 points where the first derivative is 0 and 2 points where the second derivative is 0. And you're going to then break up your number line at 0, plus and minus 1 over root 6. The 1 can either go inside the square root or outside at this point, because this square root of 1 is just 1, right? So that can go in or out, like that. Okay, so this is what I'm suggesting, that you break this up. Then what you're going to do is you're going to figure out where the first and the second derivative are plus and minus. I guess I didn't leave myself quite enough room to make this nice. There we go. And so what I'm going to do is look at like a mini graph over here to sort of figure out this is breaking up into these three roots. You know, 0, 1 over root 2 minus 1 over root 2. And because nothing funny is happening, we know from how we deal with quick plots that if we were to plot this polynomial, that would just go ding, ding, ding like that. So there's nothing fancy going on. So it starts positive, it goes negative, positive, negative. And so if I take that information and put it over here on this plot, I start positive until I hit 1 over square root of 2, and then I go negative until I hit 0, and then I go positive until I hit minus 1 over square root of 2, and then I go negative. Okay, so that much I know. And now I want to do the same kind of analysis down here for this guy, and this is just a parabola. This is no big deal. And this is a parabola. In fact, you can just think about this. X, it's like x squared minus 1, really. You're just getting a parabola that does that. So it's going to go plus, minus, plus. So it's going to go plus, minus, plus, and the switch points are going to be 1 over root 6 and minus 1 over root 6. So let's superimpose that information on our little grid. It's going to be plus until you hit plus 1 over root 6, which is here. Then it's going to go minus until you hit minus 1 over root 6, and then it's going to go plus. Okay, so we've taken all this information. Now what do we do? Well, we have this little memory tool that looks like a circle, but there we go. Okay, and we're going to remember what this meant. This meant that this little piece of curve, these are our 4 curve prototypes. This is specific to my course, and you won't get this in a calculus textbook unless or until I ever write one. Alright, so this is, the first derivative is positive, the first derivative is negative. This curve is going down, so the first derivative is negative, and this curve is going up, so the first derivative is positive. But this little piece right from here to here, it looks like an upside down cup or an umbrella. It sheds water. So the second derivative is negative. And this little piece, both of those pieces look like a cup. So the second derivative is positive. Now you just look at the prototypes and you mimic the curve shape so you know what's happening. So minus plus looks like this, so it's going to look like this. Plus plus looks like this. Plus minus looks like this. Minus minus looks like that. Minus plus looks like this, and plus plus looks like that. And so at this point you're safe to classify your points. For example, this is a min, this guy's going to be a max, this guy's going to be a min, whoops, right here is a min, and then these guys where the curvature switches from spilling water to holding water, these are going to have to be points of inflection. So at this point you're safe to do that. Now we can put it all together to make a plot, and at this point we would like to have information about f at these critical points and points of inflection and so forth. We only do as much as we can that it's not overwhelming. Oh, I'm going to erase this just to save space, but that would still be on your page if you're my student. Okay, so I'm going to calculate f of 0 because it's easy. And I would like to know, I know f of 1 and negative 1 happen to be 0, but I don't care right now. F of 1 over square root of 2, well, what's this going to be? If all I'm doing is making a little plot, then I don't care if it's perfect. I mean, actually it's really easy because 1 over square root of 2, if I square it as 1/2, I square it again as 1/4. So it's really 1/4 minus 1/2, which is minus 1/4. But let's pretend like you're in exam mode and your brain isn't working. It's a pretty good assumption. When I'm taking an exam, my brain isn't always working. Okay, so 1 over root 2, 1 divided by, there's no square root button, so I'm going to say 2 to the power of 0.5. It gives me the right value. Okay, 0.707. So I'm going to raise that to the power of 4 and subtract 0.707 to the power of 2. And I get, it's actually negative 1/4, but let's say you didn't know that. You can say, well, you'd be rounding it anyway, negative 0.25. It would be close enough. Okay, what about f of 1 over square root of 6? Likewise, the fractions are not that overwhelming. You're going to get minus 5 over 36 if you do that. And I'm just going to say, what is 5 over 36 anyway? So the answer you'd get if you just plug in, you're going to get negative 1.39, let's say. 0.139. Okay. But how would you do that? You would say 1 divided by the square root of 6 is going to be whatever that value is, 0.408. I'd save at least that many digits. 0.40825 would be better, 0.40825. And then you would raise that to the fourth and subtract that same 0.40825 squared, and then you would get something close to 0.139. Okay. Now, I'm not going to bother calculating whether it's plus or minus, because actually this function, you're going to get the same thing. The negative signs are all going to disappear. This function is symmetric about the y-axis because of the symmetry. I don't have to test both points. But let's say you didn't recognize that, then you go through and do the whole same thing again with the negative signs and be like, oh my gosh, it's like they're equal. Ha, that's cool. All right, so either way, you get those points. Now you want to start plotting these guys. Okay, f of 0 is 0, and then it plus and minus 1 over square root of 6. You're going to get some negative value, and they're somewhere here. This is good enough. And the important thing to me is that you realize that negative a quarter is lower than that. Now, whether you decide to make these guys collinear or not, I don't really care, as long as they're symmetric with respect to this y-axis here. All right. Now the last thing we want to do is put in these curved pieces. So you notice that this curved piece from negative infinity to our min point is going to be this shape. And I haven't been really great about drawing it because, well, there we go. It's much easier to do this on a computer. Blink. So I'm going to use this piece, then I'm going to use this little piece, right, this little piece, and this little piece. And so all the little pieces fit together, giving us exactly the curve we started with. We happen to know this is 1 and negative 1. And so students sometimes ask me in my class, do you need to label the x and y axis? And the answer is yes, but only if you haven't given me sufficient information elsewhere in the question. So for example, here, I'm giving all this information here, and between all that information, you don't need to duplicate that for me on the graph. But if you haven't written that information down, or you're not being very systematic or careful or neat about how you're writing it down, it's always a good idea at that point to then put the information on the plot so I can find it. So for example, I could label this, since this is my min, this could be this value, and then minus a quarter. I could label that here and say that's a min. Okay, and then I've put all that information where it goes. And maybe this is 1/6, and then it's a minus 0.139. I don't care if some things are numeric and some things are exact. That's fine. As long as you're giving me reasonable information, then you're telling me that's a point of inflection. That's all. You know, if you have been sloppy about how you're recording things, then this is a good place to just put this. You just say that's a max, that's a local max. That's fine. And I'm not too concerned about whether you're calling it a local min or max. In fact, these guys are actually absolute mins, or otherwise known as global mins. These guys. Yeah, so if you want to be really lazy, since this is symmetric, you can just do that. Okay, or you can be really lazy like that. Then you've labeled everything. Okay, so you need to label things one way or another, and if you choose not to label them that way and not to put them there, like up above like I did, then you can do something like this. You can say, well, this is at negative 0.25, and this can be negative 0.139. That's very sloppy. I need to fix that, but there we go. Well, anyway, student work is sometimes sloppy, so I will give it full credit. I'll just go ahead and leave it there. But you would still then label these as PIs, mins. Yeah, but then you'd want to put these guys in here. So what was that? This was this value. Whoops. and this one. Okay, so any of these options are good ways, and then you put them over here too. So you can either label directly on the axis, or you could label directly on the points. Or if you don't label on the points, you put the information elsewhere in the question and make sure it's all connected. Make sure that it's clear to me what everything is. So rather than, I'm not a stickler on where you put the information so long as you put it somewhere and it's clear. And in this case, I've gone overboard and put it in multiple places, which is totally fine. Some of the best submissions have the same information in multiple places. Just make sure when you copy the information you don't make a copying error, because that's another source of point loss. Somebody trying to be very neat and orderly, and then they just take, you know, like 1 over square root of 6, and then they write it like, I don't know, they make a mistake copying it. They'll you know, go something like this, and then it's wrong instead of writing it like that. Okay, so if you are making copies of things, try to be careful with the square root symbols. Okay, that's probably enough information.